Okay, I'm ready. I think we have 4.2 is due today. So, questions on the homework? Questions? On 4.2?
Number 17.
What did that say?
Show the set of continuous functions f equals f of x on a, b such that the antiderivative of f of x dx from a to b equals 0 is a subspace of C a prime of b.
So you want all the f in C, A, B with this property. We need to show that this is forms a subspace. Okay, how do we prove something is a subspace?
Have to make sure it's enclosed under addition and scalar multiplication.
Okay, yeah. 1, closure under addition. So basically, let f, g be functions on this set such that the integral from a to b of f dx is equal to 0 and integral from a to b of g is equal to 0. So I picked two elements in this set that has this property. I want to show that their sum has the property. Then this means that the sum f of x dx plus g dx. This would just be 0 plus 0, which we know is 0. But we also know by the property of integrals, this is the same as f plus g dx. This means f plus g is an element of C, A, B, with the integral of f plus g equals 0. 2, one includes closure under a scalar multiplication. So suppose I don't want to be writing this down all the time. I don't know if they gave this thing a name, but call it something like set S. Suppose f is in the set S, meaning it's a continuous function on AB whose integral is 0. Okay. Then if I take the integral of k times f of x dx from a to b by properties of integrals, this is just k times a to b of f of x dx. This is just k times 0, which is 0. And this implies that k f will be in S. This implies S is a subspace. Other questions? Is that clear?
Yeah.
Yeah, so once you're asked to prove something is a subspace, you only need to verify two things. So just show that when you add something according to the definition of addition in that set, and when you take the scalar multiple of something according to the definition of scalar multiple in that set, you get something else that's in the set. Once you have that, you have a subspace. Other questions? 2 wasn't so bad. All right, you guys can pass with the homework. We will finish 4.3. Is talking about linear independence. Define linear independence for me. V1 up to Vn are said to be linearly independent if what happens?
If you have a set of constants C1, B1 up to C and D, and with one of them being equal to 0, so it's
Equal to the 0 vector. Yeah.
yeah, so that means if it be independent, that means that one of the CNs, if it's equal to 0, then the whole thing will be 0, which means that's linear. As in C1 equals C2 equals Cn equals 0.
Okay, so it's linear independent if the only solution, that's super important, to this equation is C1 equals C2 equals C3. All of these guys have to be 0. That's what means to be linearly independent. If that happens, this is a theorem, then it means that you can't write any one as a linear combination of any of the others, right? Which is the important idea. Right? Because the idea is, let's say one of these C's were not 0. For example, let's say C1 wasn't 0. What I could do is I could bring everyone else to the other side and then divide through by C1. And I'd be able to write V1 as a linear combination of the other guys. Right? Which means, ultimately, V1 is redundant. Right? He didn't add anything, right? Because I could create him from what I already have. Right? This makes him redundant. So we don't like this redundancy for several reasons, which we will probably get to later. So whenever the only solution to this is everyone is 0, that's something that we'd like to happen. And when that happens, we say that the vectors are linearly independent. Okay. So I believe I defined that for you. And I gave you the example that the ENs were linearly independent on Rn, right? We mentioned that. Did we finish the example about the vectors in R3 that were linearly independent versus dependent? I know we didn't get far, but I don't remember if I did much more than define terms. So let's actually do an example where we're going to try to use this definition to figure whether we have linear independence or not. Are the following set of vectors linearly independent in R3? So here's A. Here's my first vector, 1, 2, 1, 0, 1, 1, minus 1, 0, 1, and B, 1, minus 1, minus 2, 2, 1, 1, 0, 0, 1. Okay, so A, what do we have to check? But what we want to do is find the solutions. Two, you're going to take C1 times V1, 1, 2, 1, plus C2 times V2, 0, 1, 1, plus C3 times V3, which is 1, 0, 1. I'm going to set that equal to the 0 vector, which is...
that yesterday. Sorry. I think we did that yesterday.
Yeah, we did.
We did A and B?
Yeah.
Yeah, we did it.
Oh. I thought I asked you guys, we did this yesterday. I think that's what we did.
So you didn't write the part, so you didn't write that.
It was that.
Oh, okay. Well, that's good.
You have to skip the reducing equation of 4.
Right, and I wrote down the matrix and I showed you, oh, 1 is determinant of 0, blah, blah, blah. I think I probably mentioned that. Okay, good. All right, we got farther than I thought we did. That's good. And I spoke about the linear independent set in Pn.
No.
In Pn. What's Pn, by the way?
Polynomials.
Okay.
Of degree n.
At most degree n.
At most degree n, right? This is polynomials with degree n or less. The vectors 1, x, x squared, x cubed, all the way to xn are linearly independent. So that's another example. If I say C1 times 1 plus C2 times n plus C blah, 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 set that all equal to 0, the only solution could possibly be all the C's equal 0. That you can check, it's not hard to show. I don't really care about that either. Okay, so this we have mentioned before. Well, sort of. I kind of spoke about basis. Let S equals V1, V2, VR. Be a set of vectors in Rn if, well, we sort of did the flip side to this. If R is bigger than n, then S is a linearly dependent set. So for example, if I'm looking at R3 and I give you 4 vectors, for example, then I will get a linearly dependent set. Let me see why that is. Or do you verify something like that? How do you prove that these guys form a linearly dependent set?
Write out the C1, B1 plus.
Yeah, okay. So we'd go C1, B1, plus C2, V2, plus C3, V3, plus C4, V4, equals the 0 vector in R3. Well, what would that mean?
If you have one of the C's they're not equal to 0, that means that would be linearly dependent, right?
Yeah. What would happen here? How would I go about showing that this is linearly dependent? Yeah?
Wouldn't you be able to subtract, like for example, one of the C's to the other side? That would mean that it would be negative C4. C4, for example, that would mean that the C4 is not because of negative 1, which means it's not linearly independent.
Well, what if C4 was 0?
And you'd have to do that with like all the C's.
Yeah.
No? How about thinking of this? Let's say you think of V1 as the vector ABC. This is the vector DEF. This is the vector GHI, JKL. So what would actually happen here?
Actually, you can span with the first 3 vectors. Probably you can span all the R3. The fourth one is
Well,
n.
follow the definition. When I write this out, what am I actually getting now?
The sums of these would give you the 0 factor.
Ultimately, what would I get?
In the matrix form.
In the matrix form, what would it get? What would it look like in a matrix if I threw it in a
0
matrix?
C1, B1 is
C1,
equal 0,
C1,
C2, B2,
You would have a non-square matrix.
You'd have a non-square matrix. Yeah, what would the matrix look like?
4 rows, or 4 columns, depending on how you arrange the vectors.
3 rows and 4
That would
columns.
be
One
two
column,
columns
A,
and
B,
4 rows.
right?
One column is A, B, C,
And that's it.
DEF,
D, E, F,
Keep going. GHI.
G, H, I, J, K, L, and then this would be 0, 0, 0, right?
Yeah.
Now, why is this a problem?
It's too many variables.
One of the
There's more
columns is going to be
The parameter.
parameters,
There's more nodes in the equation.
parameterized.
Now, remember what we want to disprove here is that the trivial solution is not the only solution. I know the trivial solution is a solution. If I plug in 0, 0, 0, 0, I definitely get something. So what is the only other case? What is the only other thing I'd want to show?
Infinite.
They're
So-
infinite.
That it has infinite solutions. How do you know that this has infinite
because
solutions?
there are unknowns more than the equation in the previous
Fine.
Yeah, so what would that mean?
It means that this is infinity solutions, more than a single solution.
Only give parameter should be equal to jar.
Yeah, there could be a row of variables. At most here, you will have at least one free variable. Right? Basically, the best case scenario would look something like 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, right? That's like the best case scenario. That's when you try to not make there be a free variable. That's the best case you'll have. But this column won't have a pivot. Right? So you can have at most here 3 pivots, right? But you have 4 variables, which means one variable has to be a parameter, which means there's an infinite number of solutions, right? So here we know that solution is not unique, which means there would be an answer for C1, C2, C3, C4 where not everyone is 0, right? No matter what choices I make for these components here. So it's important that you can think through these things based on definitions and then bringing it to something familiar that you know how to deal with. Okay. Thought I'd mention that. Here's an example I want to do. in the set, sometimes are the functions f1, f2, 3. Linearly independent. Do those form a linearly independent set? What do you think?
No, doesn't.
Why not?
Pull it out fast.
Because cos 2x is cos square minus sin square.
Okay, we know that cosine 2x is cosine squared x minus sine squared x, okay?
And f3 is cos square plus sin square.
Cos squared plus.
1
Cosine
is
squared plus
cosine
sin squared.
cos square plus sin
Okay.
square is 1.
Yeah, so
Then
what does that give us here? We can just replace cosine squared with 1 minus sine squared, right? So this is basically a trig identity. And so now what that actually means is if I have 1 times cosine 2x plus 2 times sine squared x minus 1 times 1, I will get 0, right? Which means if I look at this guy as my C1, that guy as my C2, this guy as my C3, I've found a non-trivial solution to a linear combination of these functions, right? Here it's easy, or it should be easy, because we know an identity. What about in general? Right? What if we're in the space of functions and I want to know if a random list of functions, which I might not know an identity that connects them all, are linearly independent? Right? I give you a random list of functions. How do you figure out if they're linearly independent or not? Well, I'm just going to tell you. Well, some calculus is required here. N plus 1 differentiable. We can call this C to the n minus 1 functions are linearly independent using what's called the Wronskian. Now, those of you who have taken 391 differential equations before, Wronskian, will already know what this guy is. And they'll just say, oh, compute the Wronskian, and this is not 0. Blah, blah, blah. This is why the Wronskian was important in 391. It was a way to tell when functions were linearly independent, because in 391, finding linearly independent solutions to a differential equation was pretty important. Wronskian was often a tool that you used to be able to tell if they were linearly independent, right? So given n functions that are n minus 1 times differentiable, what you would do is you would set up the system. First, there's a system that's of interest. You set up C1 F1 plus C2 F2 plus da 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 Cn Fn equals 0. That's what you really want to know what the solutions to that are. But what you do instead now, you differentiate this equation n minus 1 times. So the next equation, I'm going to have C1 F1 prime plus C2 F2 prime plus Cn Fn prime. And I'm going to do this n minus 1 times to have C1 f to the n minus 1th derivative plus C2 f to the n minus 2 derivative plus Cn f to the n minus 1 derivative of these functions. And so we end up with here an n by n system. Right? Because there are n rows and there are n columns from the functions. This gives, if you look at this as an augmented matrix, you realize that what you have is F1, F1 prime, all the way down to f to the n minus 1, F2, F2 prime, all the way down to F2, n minus 1, Fn, Fn prime, all the way down to Fn minus 1, 0, 0, 0. The coefficient matrix here is called the Wronskian. It's named after the mathematician that came up with it, Joseph Wronskian. And for emphasis, you can say it's the Wronskian of the functions F1 to Fn. And notation for this is a big W. You say W of F1, F2, up to Fn. Or you can call it just W if understood what the functions are.
So professor, it's like the same thing in 391 where instead of using fundamental set of solutions, you just use the function you're given?
Come again?
Like in 391, like you use the Wronskian when you have like a fundamental set of solutions, but in here you just use...
Well, you'd use the Wronskian to see if a set of functions you have is a fundamental set of solutions.
Right, so the items you're plugging in here, you just gotta, they're the same functions you just gave some at the beginning, like those 3 or 4, right? You could just plug them in and just take
Yeah,
care of
I
it.
could have done that.
Alright.
Right, I'll probably actually do, I wasn't going to do that example, but I could probably actually do that example. Okay, so, but what am I getting at now? So now if I look at the coefficient matrix, what conclusions can I make? What would I look for? This means, tell me some things that we can conclude here.
All the derivatives also has to be here.
Yeah, but I want to focus on these guys. How would I know if these guys are linearly independent? The original functions. What would have to happen? Give me a condition that would force that to happen.
The coefficients would have to all be 0, right?
Yeah, how would I know if the coefficients are all 0?
Define determinant.
Determinant?
Yeah.
What about the determinant?
find it?
It doesn't equal 0?
Right. Now if I look at the determinant, well, technically the Wronskian is already the determinant. This is actually the determinant of the coefficient matrix. Didn't just want to tell you guys that, I wanted you guys to see it. This is the determinant of the coefficient matrix. This means if W not equals 0,
Independent.
then what does that mean?
Independent. If it's equal, it will be dependent.
Okay, if it's not 0, tell me why it's independent. Not being 0 means what?
Unique solution.
Then there's a unique solution.
That's the trivial solution.
Right? But we know that the 0 solution works because it's a homogeneous system. So a unique solution means that that this must be the trivial solution. Which means the functions are linearly independent. Fn are linearly independent. Right? Obviously this means if W is non-zero, if W is 0, they are dependent. Because we know a solution exists, so the only other option would be infinite number of solutions. So this system is always consistent, but it's just a question of whether it has one solution or infinitely many. If the determinant is non-zero, it will have one. If the determinant is 0, it has infinitely many because it's a homogeneous system. Right? So back in 391, and probably not everyone took that, but finding all solutions to the differential equation was really important. But the thing is, you can prove that if you have two solutions to a differential equation, then a linear combination of them is also a solution. And so when you have a list of functions that solve this thing, you want to know, are there any solutions that are redundant? Or is this the most number of solutions that we can have? The Wronskian was one of the tools you used to check this fact. And just as how with a certain dimensions, you know that if you have more than a certain number of things, that was it. You would have a dependent solution. In the same way here, back in differential equations, you could realize something like a second order differential equation can have at most 2 linearly independent solutions, right? If you go one further, you end up with a row of zeros when you transform everything to a matrix, and then you get infinitely many. So once you have like 2 solutions to a differential equation, and then you check the Wronskian and you get it's non-zero, it means those are the only 2. You don't have to look for any more. And that was really good. Differential equations can be really difficult to get a handle. But basically you use linear algebra to figure out how to let the solution behave. Thought I'd tell you about that. So that's called the Wronskian. So, let's do an example. Simple example, of course, sines and cosines are linearly independent functions. So i.e. c1 cosine x plus c2 sine x equals 0 will only have the trivial solution. Now you might not be able to actually solve this directly, mean, there are ways you can figure it out otherwise. You know, if you really know a lot about the graphs, you can use calculus and figure this out. But let's actually do something a lot cleaner, like the Wronskian. So here, the Wronskian of cosine and sine would look like what?
It's gonna be a 2 by 2 matrix.
It's just going to be a 2 by 2 matrix.
with
So there's the
sine
cosine, its derivative,
Minus sine x, and then
sine, its derivative, it's that determinant. Now if I take the determinant of that, what do I get? Cosine squared x plus sine squared x. But that's just 1, which is non-zero. Cosine, sine are linearly independent. Which means the only solution to this equation is the trivial one. That was the last thing in this section. So, basically, I'll be summarizing the theorem. Suppose f1 to fn are functions in Cn-1. You don't always have to look on an infinite interval, but you can talk about being linearly dependent in a given interval, but let's just make it as big as possible. Go big or go home. Then, we know that f1, f2, fn are linearly independent if and only if the Wronskian of f1 to fn is not identically 0. On the interval of consideration. So in differential equations, they would have told you that, but they wouldn't really have told you why. But now with chapter 1 from linear algebra, we actually know why. So I was debating whether I wanted to move on to 4.4 or talk about something else. I'll probably just talk about something else. Really quickly, very informally, which is ironic since it's about, the subject matter is about being formal. First, tips and how-tos. 1. So in this class, and now it's going to be far more common, we're going to be asking to prove things all the time. Actually, in the first test to prove a lot of things, and I saw a lot of things that were concerning. So I decided I'd try to talk about them. So let's talk about proofs. 1. How do you get good at proofs? The first thing you want to do is know your definitions. The only way to prove that, I say, oh, prove that this is blah, right? The only way you'll be able to do that if you know what blah actually is, right? So the first thing is to actually know your definitions. That's super important. It's not just for proofs. That's like in general. I mean, I've had students in lower level math classes where they ask me questions and so what do you think we should do? I don't know. I'm just confused. Okay, well, what does that mean? And they can't tell me anything. You know, it says I have to find two vectors that are orthogonal, two unit vectors that are orthogonal to this other vector. Okay, what does orthogonal mean? Okay, well, what's a unit vector? Okay, do you know how to tell if a vector is orthogonal? Right, so of course you're going to be confused if you don't know what the heck you're talking about, right? I can tell you the simplest instructions. I can say, get out of your C and go sit over there, but if I tell you in a language you don't understand, you won't be able to do it, right? You need to understand the language, you need to know the definitions, you need to know what it is. So usually when I ask you to prove something, I'm going to say, prove that these are linearly independent. You need to know what does it mean to be linearly independent, because that's the goal, right? You always need to know your goal. So that's where you first want to start. You want to know your definitions. Super important. Two, avoid. I'll talk about some of these logical fallacies. Now it might sound weird, but a lot of times, in order to get something right, all you have to do is avoid being wrong, right? Which sounds funny, but it's actually true, right? Once you don't do anything crazy, sometimes just following your nose gets you to the answer. You need to avoid certain logical fallacies. Some of them that I saw in the test, for example, was something like, some examples, begging the question. This is a very big one. It's called begging the question. This is a fallacy. Meaning it's wrong. You can't do it. It doesn't work. This is, anyone knows what begging the question means? No. I didn't say begging for questions. Begging the question is assuming what you need to prove. And I saw a lot of that. So I might say something like, prove that if A does this, then A is the identity. And if you start out, assume A is the identity. Right? I just asked you to prove that it's the identity. You can't start by assuming it's the identity, because that is called begging the question. Right? And you write something like that, and really nothing else you say matters, because if you assume that that's true in the first place, then everything you write are going to justify that. Right? It's not going to be a real proof. Right? So at that point, you're just like, no, I'll just exit out and just stop reading. Right? So be careful not to do that, to assume what you want to prove. 3 is know how to prove certain statements. Right? So each statement kind of has a technique that goes with it. A very common type of statement. A very common type of statement is the implication. Now, what does the implication look like? Let's say P, Q are declarative statements. Right? So there are statements that claim something to be true or false. Right? Then an implication would be something like P implies Q. Or I could say something like, if P, then Q. Right? Or you might see in symbols, P, you'll have this arrow thing, and then you'll have Q. Or you might see Q if P, something similar to that. And these could be anything. So for example, in the test, I had a question like, if A transpose times A equals A, then A is the identity, right? So P would be the statement, A transpose times A equals A. Q would be the statement, A is the identity, right? So this is a very common type of statement. A lot of statements look like this, and if not, a lot of times you can reword a statement to look like this and it actually be equivalent. So that kind of statement is a very important kind of statement, and it lends itself to a lot of techniques. So, if you know how to prove this sort of statement very well, you're well on more than halfway to being an expert prover. Okay, techniques for P implies Q. There's one thing called a direct proof of P implies Q. Essentially, P implies Q means if P is true, then Q must be true. So a direct proof involves now this statement can be right or wrong. You can disprove a statement, which we'll talk about soon. But let's assume P implies Q is a true statement. How would you actually prove that it's true? The direct proof says do the following. 1. Assume P is true. 2. Show that Q is true as a consequence. Right. Of course, I'm talking about logically, mathematically valid means of going from step 1 to step 2. Right?
How is that not begging the question though? Because you said like assuming what you need to prove, but you need to prove that P is true and Q is true.
No. I need to prove that if P is true, then Q is true. I don't need to prove that both are true.
Oh.
It's actually it's a very different statement. So for example, I can say, it's kind of like you think of it as a contract. So I can say, if you get a 98 on your test, I'll give you $100, right? So I can say, if you get a 98 on your test, then I will give you $100. There's nothing to say that both of those statements have to be true. It's just saying, if one happens, then you expect certain consequences from that thing, right? So what I'm trying to say is, begging the question in this case is to assume Q is true, right? Without actually showing that it has to be true, right? You want to assume, pretend this happens, then you expect something else to happen. If you just assume that that thing happened without actually justifying it, then that's called begging the question, right? Begging the question in a case like P implies Q would be assuming Q is true. Q is the consequence, Q is the conclusion, Q is the end point, Q is the goal that you want to get to. You can't assume that you're there, right? So let's maybe do an example. First, let's do some definitions. I'll start with some simple examples and then we can move on. What does this mean? Let A be an integer, right? We say A is even if, how do I know that an integer is even?
It's a multiple of 2.
It's 2 times another integer, right? It's 2n for some other, or some n z, right? That's what even means. Definition. Okay. Let A be in Z. A is odd if we say that A is 2n plus 1 for some n in Z. Okay? That's what even and odd means. So that's a definition, which means anytime someone asks you to prove anything about being odd or even, that's what you should think about. You need to show that that's true. So for example, I can make the statement, prove that if A is A and B are even, then A plus B is even. Right? Prove that if I add two even integers, I get another even integer. How would you actually prove that? Well, doing a direct proof, the first thing you would do is you would assume P, right? Now in this statement, what is P?
A and B are even.
A and B are even is the statement P, right? That's your P. What is the Q?
A plus B is even.
A plus B is even, right? So I want to know, if I know a priori that these two are even, then I should be able to conclude that their sum is even. If I start out by saying, assume A plus B is even, I'm already wrong, right? I cannot assume this. This is what I want to prove, given that, right? So what would I do here? I would assume A and B are even, right? Immediately, what does that mean? A is 2n and B is 2m. They could be different, or n, m, and z, right? So I start by assuming this. I write down what that means, and now I want to use that. Then A plus B would be equal to what? Well, 2n plus 2n, which is 2 times n plus n. And n plus n, the sum of two integers is an integer. We know that the integers are closed under addition. So this means A plus B is even, right? You can't just tell me that A plus B is even. You have to show me that A plus B is 2 times some integer, right? You have to show me the definition of what it means to be even. That's how you prove something, right? Because, well, A plus B has to be even, right? Because if I had 2 and 2, if I had 4 and 6, right? You can't actually, which is another big mistake, I should have probably written that down in the fallacies. You can't actually prove a general statement by giving me examples, right? You can run into a lot of trouble by doing that, right? Because then you can be like, well, you know, 3 is prime, 5 is prime, 7 is prime. Well, that's the first 3 odd numbers. All odd numbers are prime, right? You can't do that. You can't just tell me about a few examples and then make this general declarative statement, because it's wrong. The very next odd integer is not prime, right? So just giving me some examples does not work, because there's always the case. What if you missed one that actually messes it up, right? So you have to prove by definition, and definition means you have to show me that this is 2 times something, because that's the definition of what it needs to be.
So to prove something is false, all you need is one example, right?
Yeah. Right, so usually when these statements, it's sort of saying these guys are all encompassing. I'm saying that if A and B are any even integers at all, then their sum has to be even, right? I don't care which ones you pick, right? So if you can just show me one example where that's not true, then this is already false.
Q is false, then false.
Another technique is called proof by contrapositive. The contrapositive of P implies Q is the statement. I actually don't know why they call it a contrapositive, but that's what it's called. Q implies not Q implies not Q. Right? I'm not going to prove this to you, but I'm just going to say these are logically equivalent statements. You can prove this using truth table. If you ever did a logic course or a basic proofs course, they would have done that. Logically equivalent statements. Meaning they'll both be true or both be false at the same time. You can prove one by proving the other. Right? So one way to prove that if P then Q is to assume that Q is not true and then show that P is not true. So if I do what proof by contrapositive, step 1, assume not Q. That's a symbol for not Q. It just means assume Q is false. Right. 2, show that not P is a consequence of this. That is, P is false. If you do that, you say you've done a proof by contradiction, by contrapositive of P implies Q. So why would we want to go that way? It's also called an indirect proof. Why would you want to prove something indirectly? Well, it depends on the statement. So for example, I could ask you, prove that if A squared is even, then A is even. I could ask you to prove that statement. Now, if you try to do this by a direct proof, you'd run into trouble, right? So you might have, if you tried it directly, what would have happened was, you'd say, assume A squared is even, right? So this basically means that A squared is equal to 2 times some integer, right? How would I figure out what A is? I have to take square roots. Right? Now, really, there's no way I can really tell that that's an integer at all, right? It has a radical 2 times something. So if I just jump into a direct proof with this guy, I get to a point where I'm like, well, it has to be even. I mean, you can think about it. Yeah, no, that's not proving anything. That's not a consequence. That's not convincing anybody. To prove that that's an integer, that's going to be really hard. So a direct proof would be actually really difficult to do here. But look here. Yeah?
Can you square that if I say even number squared is even?
An even number squared is even?
Yeah, I mean 2 times
Yes. In fact, this goes both ways, which when I talk about biconditions, we talk about. You can actually prove that A squared is even if and only if A is even. So yeah, it goes the other way as well. But getting to this point wouldn't actually help you. So directly wouldn't be the way you'd want to go. And the trick would be the statements themselves. Dealing with a square integer is a lot harder than dealing with just an integer itself. So here, notice that the Q statement is actually the simpler statement. So I probably want to deal with this one, right? But again, remember, I can't beg the question. I can't assume Q. However, I know that this is true, so what I can do is just assume this is false, right? So if I wanted to prove this kind of statement, I would say something like, assume I'd assume that A is not even. So I assume A is odd, right? So I'm going to the Q statement, and what I did was I assumed not Q, right? If it's not even, it's odd. So this means that my A is, what does odd mean? Well, it's 2n plus 1 for some integer n. Well, then that would mean, if I square it, it's the same as squaring this guy, which gives me 4n squared plus 4n plus 1, which is actually 2 times 2n squared plus 2n plus 1. Now this guy here is an integer. Because I know the product of 2 integers is an integer, and if I take the product of that is an integer, and if I add 2 integers, I get an integer, which means A squared is odd. But A squared is odd is actually the opposite of this statement, right? This is actually not P. And we're done, right? Because I just showed that not Q implies not P. This is called a proof by contrapositive. when we get to the next section, I think we'll actually do a proof like that. Using both of these. There is what's called a proof by contradiction. To prove P implies Q by contradiction, means assume P implies Q is false. Then show that this leads to a contradiction. I.e., step one in a proof by contradiction. How would P implies Q be false?
Only if Q is false.
If P is true and Q is false, right? So if I made the statement, if you get a 98 on your test, I'll give you $100, and you get a 98 on your test, but I don't give you $100, I made a false statement, right? That's the only way for me to make a false statement, right? So it's like, if you don't get a 98 and I didn't give you $100, you can't say I lied to you because you didn't get the 98. I don't owe you anything, right? The only way for me to make a false statement is if the first thing happened but the second one didn't, right? So in one, what you would do is you assume P is true, but Q is false. This is the same as assuming not P implies Q. And so the second thing you'd want to do is to show that that guy, not P implies Q, that actually leads to C, which is a contradiction. Now the thing with proof by contradiction is it's a super broad kind of proof. I mean, it could be a contradiction in anywhere in all of math, right? So I could be proving something about, I don't know, circles, and then I end up with 1 + 1 = 3, right? So something that has nothing to do with circles, as long as something breaks somewhere in math, you can do a proof by contradiction, if you can somehow find a connection to it, right? So it's a really broad thing, but sometimes it's actually not that hard to get a contradiction. Right? Any contradiction. Right? Sometimes I write a lightning bolt to kind of bother writing contradiction. So, example. I can even do the last one by an example, but I'll probably do another one. Prove that a squared is even implies a is even. Okay. So I can say something like, assume to the contrary that a squared is even, but a is odd, right? Now when you start a proof like that, I know you're doing a proof by contradiction. You assume the first statement is true, but the second one is false, right? Now you need to show that this leads to a contradiction of some sort. It's going to mess something up, either with this statement itself or somewhere else in math, the math universe, right? So now I can say if A is odd, right? So I'm assuming that A is odd. Then that means A equals 2n plus 1 for n, some integer n. But then what would happen there is that my A squared would be equal to 2n plus 1 squared. We did this before. This is 2n squared plus 2n plus 1 would be odd. But wait, I just assumed it was even. Now suddenly it's odd. This is a contradiction. Right? It's odd. this contradicts our original assumption. And you could end there. This is a proof by contradiction. Right? So assume what you want to prove is false, and then show that that just couldn't work. Because if that was false, then something crazy would happen. So it must be true. That's called a proof by contradiction.
Jerome,
Yes.
how would the 2n plus 1 squared be odd again? Is it equals 2 times 2n squared plus 2n?
Yeah, it's equal to 2 times an integer plus 1. Anything that's 2 times an integer plus 1 is odd, by
Gotcha.
definition of being odd.
Thank you.
Or proof by induction. And that we've actually done an example of this in class, I think, where we're proving something about the inverse of a list of products of matrices is the inverse of the matrices in reverse order. I think we did that with a proof by induction. So Pn is a statement that depends on n. Usually, n is an element of the set of positive integers, 1, 2, 3, so on. Right? But sometimes they start from 0, but whatever, it will apply here. Prove Pn is true for all n in that set. The one, show that P of 1 is true. Right, so I prove that it's true for the first guy, that statement, whatever it is. This is called the base case. Two, assume P of n is true for some particular n. Right? So it's not begging the question, it's not the entire statement. You're just assuming it's true for some particular n. This is called the inductive hypothesis. You know it's true for at least one of them, so now I'm just pretending it's true for somebody. 3, show that Pn would imply Pn plus 1. So I'm proving that if it's true for somebody, it will be true for the very next person as well. Right? And that's it. That's called a proof by induction. And we actually did an example before, so we don't have time to go over one. So something like that would be an example of a statement. It would be something like this. 1 plus 2 all the way up to n is equal to n times n plus 1 over 2. For n in n. Right? So I just made a statement for all natural numbers n. If I take the sum of the first n integers, the result will always be this. Right? This is my statement Pn. And how you prove something like that is a proof by induction. Right? Usually when you have something that depends on integers, and you want to prove that that same statement is true for all integers, then you prove that something like use a proof by induction. That would be a technique that you'd want to use. Right? So we actually use this on proving that A1, A2, AN inverse was actually AN inverse. I'm pretty sure I proved this. So you can look up what I did there. It was a proof by induction. Right? So this was a statement that depended on n, some integer. and I want to prove it's true for all of them, so I did a proof by induction. Right? It's the kind of statement sometimes you can use. Anyway, so we finished 4.3. So the homework for that is due. We'll move on to 4.4, and we'll start proving a lot more things now. So that should help you.